This conference will now be recorded.
I'm going to go on the board behind me. I'm going to ask pretty much everybody to shut off their camera because I have to make myself big in the presentation so you guys can see this board. But that's when we do this. But I have a little bit of a presentation in between, and so we'll get to that. So yeah, it's math. No, it's not pleasant, but actually I got to cover it according to the DEP. You know, many people, we forget. If you had said when you were in school that, oh, I don't know this, then because I'll never use it again in my life, I'm sorry to say this is the where you're going to use it. Now, again, in the business, you may not be doing stuff like this right away either. The DEP does require certain subjects in math to be covered, so I'm going to do that. But also in the test, there are going to be math questions. There's not going to be a lot of them. Honestly, there's not going to be a lot of them. I do know some people that have, they told me if they'd paid more attention to doing the math, they would have passed the exam. I have ran into a few people that's happened. But it's a lot of it's basic math, but we do need to do a little bit of algebra. Sometimes you're going to see problems that you're going to have to rearrange because we live in a world that isn't 100% metric. Sometimes you're asked to calculate, like for example, pounds per gallon of use of a chemical, and you're going to get lab numbers in milligrams per liter, so you have to kind of convert things over. That's really not that difficult to do. I'll show you when that time comes. Also, we're going to do some calculating volumes, areas and volumes in tanks. There are some loadings that are associated in the industry with like areas, for example, surface loading rate, surface settling rate, hydraulic loading rate. They're all kind of the same. But it's going to be measured, say, for example, gallons per day per square feet. If you're going to calculate flow through a pipe, you need the cross-sectional area of the pipe, and you're going to need the velocity in the pipe, and then you're going to get the flow. If you want to calculate the velocity in the pipe, you're going to need the flow in the pipe and the cross-sectional area so you can get the velocity. So you kind of sometimes rearrange some formulas around. Sludge pumping is kind of the same. You measure the pounds of solid, say, that's going into the tank, and you subtract it from the pounds that are coming out of the tank, and it gives you what's being retained in the sludge. And then you can kind of calculate an initial sludge pumping rate based on the stuff that's falling into the tank by picking a density that you get at the pump. Now we know that sludge densities change as you pump out of a tank, but we'll address all of that. But a lot of it is, again, conversions is kind of a big deal. And in areas, linear measurements, areas, and volumes. And I work in cubic feet, which is what we mostly work in. And then there's certain conversions going to be tattooed on your brain, like 7.48 gallons per cubic feet, 8.34 pounds per gallon. Another one is 0.433 psi per foot. And actually, somebody in the class had mentioned it, and I didn't catch on me right away. 2.31. 2.31 feet per psi, and that involves height or head pressure. For every 2.31 feet of head pressure, you're going to have 1 psi at the bottom of the tank. Stuff like that. Yes. Yeah, it was you, right, Ron? Yeah, I remember that. I think you said 2.31, and it didn't catch in my puny brain at first. But some of those things you're just going to remember. You are. It's just part of the nature of things. And so let's get rolling. I got a presentation. Again, I'm not going to play the initial video. I might have already. I'm going between this and the other class, but so I'm going to put the share screen up here. It may not play. Actually, I think I might have already get started. So yeah, let's throw this one up. I'm not going to play this video. It's because it's gonna crash the system. It always does. At least lately, it's been doing that. Let me shut my camera off. And it'd be nice if you guys, I think you all have your cameras off as well. So I know I kind of did a little bit of an introduction. Many of it, like I said, math is at the foundation of what we do. That is absolutely true. Every piece, every pump, every tank, every pipe that you've either worked with, worked in, or have seen or walked over, somewhere along the line, somebody worked something out on a calculator. There's been a big calculator. Now we're going to kind of stick to the basics. All right. Some of the simplified formulas may look complicated for you. But if you were to go like up into engineering and see some of the things that they figure out, they're going to be a lot more complicated. Actually, some of the volumes and stuff that we do, you may not get the same answer. I'll try to explain why that happens. It'll be close. It'll be in the neighborhood, but it won't be the exact number. And it all depends on, like, say, a circular tank, how they calculated, whether they use pi or did they use 0.785. And then how many decimal places to pi did they go? But at any rate, basic arithmetic skills need to be reviewed and refreshed in order to smoothly address the equations and formulas encountered in our field of study. Okay. All right. Now this, I put this up here many years ago. I actually haven't been to this site in a very long time. You guys can check it out. This Khan Academy. It was helpful for me many years ago when I was just starting to get back into the maths end of it. It may be helpful for you. He has his own website, or he did, but he can also look at some of his stuff on YouTube videos, Khan Academy. To me, he made things easier for me. It may not be the same for you. Just like if somebody where you work, there's a book floating around out there. And it is useful. It's a good book, but it says the name of the book is Wastewater Mathematics Made Easy. All right. And it covers a lot of things in the book. It covers a lot of different formulas and how to do things. I don't necessarily think it makes it easy, but that's just my personal opinion. And I know somebody's got it sitting on a shelf somewhere. I know, like today, I said I was at the seminar. I was talking to Leslie. Leslie she has books and books and books and books. I didn't mention this book, but I'll guarantee she's got it. And who knows, maybe she'll loan it to you if you ask her. She's got every book you can imagine. She's really been a student of taking her licensing exams, and anytime a book comes out, she jumps on it. She gets it, because she wants to pursue her licenses. I think she's got her 4. I'm not sure if she's got her 4 or her 3, but anyway, I know she's got a lot of books. And I'm sure there's other people down there that have a lot of books. I was talking to somebody, I actually don't know him. He's in charge of the head end, Max. I don't know, he mentioned a couple of your names. Like I said, I don't know him. He had started after I retired, and he came in as a boss, but he seems like the academic type as well. He wants people to get their licenses, and he wants people to go to school. But he did mention, I'm trying to think who he mentioned. It's neither here nor there, but a lot of these folks that are actually pushing you have a lot of resources, and maybe they'll let you borrow something, All right, so there's rules for solving equations. Now, again, this may be a review for a lot of people. Some of you folks may be really good at math, and this is just like, so what? I hope so. But if not, we'll try to work through it. Most of the equations are plug and play. That's the way I like to put at it. I think I went over the ABC formula sheets the last time. All right. A lot of times it's just plug in the numbers that they give you in the blank spots, and then you just calculate, you know, most of them. Sometimes it's not that way. Sometimes you got to rearrange the problems. And I actually have more of those, I think, in my problems to try and exercise those muscles of recognizing to rearrange the problems. But if there are some basic rules for these equations, and sometimes, again, you got to rearrange some things, and we'll get into that. And I think I remember when I went over the ABC sheets, I showed you guys the circles. They're the I hate algebra circles, and if you grasp the concept of the circles, it'll make life a lot easier. Especially, like, say you're asked to calculate the dosage based on a flow and a pound's usage. You will use the circles to do that. Or like with you, when we do a flow and velocity, the flow, the formula, and don't get shaken up, it's Q equals V times A. Q, for some reason, they decided to make that flow. V is the velocity and A is the area. But if you know the flow and you want to determine what the velocity in the pipe is, you got to rearrange that formula to solve for that V. And another thing to remember is the units all have to agree. Unless you're doing a ratio of some kind, then it doesn't really matter in that respect. But for example, if you're calculating something in cubic footage for a volume, that's a volume. It's a three-dimensional. But you may be asked to, what is that in gallons? So now you have to convert that. You have to convert it from cubic footage to gallons. Some problems it'll be, well, if you have 6 inches of rain over an acre of pervious, say a parking lot, an acre parking lot, and you have 6 inches of rain, all right? An acre is 43,560 square feet. Okay, so if it's an acre, or if that's an acre, there's 43,560 square feet in an acre. If it's a half of inch, or if it's 6 inches of rain, which is a half a foot, you would multiply that by 0.5 and then take that number and multiply it by 7.48 gallons per cubic foot. And that's going to give you how many gallons fell on that parking lot during a rainstorm. Things like that. We are going to do things like that. But there are some basic rules, all right? Now, usually, usually you work from left to right, right? There is an order of operations, and that's important, especially on your calculator, because sometimes the calculator screwed things up if you don't do the proper order of operation. And I'll get into that a little more specific. It's actually written at the bottom. PEMDAS, please excuse my dear Aunt Sally. But for the most part, you do all the multiplication and the division. Usually, of course, you would be multiplying across, and then you would do the bottom. Sometimes you do the bottom first because there's actually something to do, all right? But that multiplication across the bottom, across the top, that line in the middle, all right, of an equation, that line between the top and the top is known as the numerator, the bottom is known as the denominator. That denotes division. Okay, that denotes division. So if you do what's on the top, then you would do what's on the bottom. You divide the top into the bottom, you're going to get an answer. All right. Now, parentheses you always do first. Parentheses you do first. You do those first. All right, because the parentheses and brackets are what separate different parts of the problem or the equation, right? So you work the arithmetic within the parentheses before working outside the parentheses. And you use the same order stated in those previous rules, usually work left to right, above and below the line, and divide the top number into the bottom number. Now, you might have all went to school and you've heard this acronym PEMDAS, or please excuse my dear Aunt Sally. There's a method, and it's basically called order of operations. It's real important because you can get the wrong answer if you don't follow PEMDAS. And the first one is parentheses. Always work within the parentheses first. Exponents. You always calculate exponents. So what the heck's an exponent? If you have 3 with a little 2 above it in the right-hand corner, right? That's the same thing as saying 3 times 3. That's the number multiplied by itself. If, say, you have a 3 and a little 3 above it, that's known as 3 cubed. That's 3 times 3 times 3. That's would be 3 times 3 times 9 times 3, which is 27. That little exponent is denoting that that number is being multiplied by itself that many times. That's an exponent. All right. So you do those things first. Then you do multiplication and division first. And I have a little video. I think this one's going to play. So you do the multiplication and division. You do the parentheses and the exponents. Then you do the multiplication and division. Then you do the addition and subtraction. It's called an order of operations. After a while, you just do it. You don't really think about it, but that's the structure. And you can get the wrong answer if you don't follow the rules. Right. And this is I think this guy's like a middle school teacher, or maybe it's probably elementary school. And I think it's going to play. Let's see. If it crashes, it crashes. I've kind of explained what he does, but he has some specific problems that he goes over. And let's see if this works.
Hi. Right now you're going to learn one of the most important rules in math, and that is called the order of operations. We always have to follow this rule in order to solve math problems. If you remember this acronym, PEMDAS, then you will remember the order of operations, because each letter in PEMDAS stands for something that you need to do. P stands for parentheses. E stands for exponents, M and D stand for multiplication and division, and A and S stand for addition and subtraction. And this is the order that you need to do things in. Parentheses first, exponents next, multiplication and division from left to right, and then addition and subtraction. We always have to go in this order in order to get the right answer. So let's take a look at a problem here. 3 to the second power plus 8 minus 3 in parentheses times 4. In order to find the answer, we have to follow the rule. So the rule says, PEMDAS, first we're going to do parentheses. So I'm going to look in this problem and I'm going to see that, oh, here's parentheses right here. So this is what I do first. 8 minus 3 equals 5. So I'm going to write that down. And now I'll just copy down the rest of the problem. 3 to the second power plus 5 times 4. I did parentheses first. There are no other parentheses in the problem, so now I'm going to move down. I'm going to do exponents next. And I look at this problem and I see, oh, there's one number that has an exponent. 3 to the second power. 3 to the second power, if you remember, that means 3 times 3. So 3 to the second power actually equals 9. 3 to the second power. So then I just write down the rest of this. Okay, now I have 9 plus 5 times 4. Well, I've done parentheses, I have done exponents. Now I'm going to do multiplication and division from left to right. So I will start here, and whenever I see a times sign or a divided by sign, I will stop. Oh, there's a times sign right there, multiplication. So that means I have to do this part next. 5 times 4 equals 20. And now I have this, 9 plus 20. And that's easy, because now I can do the addition and subtraction, and I get 29. So the answer to this problem, 3 to the second power plus 8 minus 3 in parentheses times 4 equals 29. Let's take another problem. let's do something like, oh, let's take something easier. Let's do 8 plus 2 times 4. And we have to say, what does that equal? Well, you would think that maybe you would just say, oh, 8 plus 2 is 10 times 4 is 40. But you would get the wrong answer if you did that, because you have to follow the rule. The rule says parentheses always comes first. There are no parentheses in this problem. So then we move on. Exponents always comes next. No exponents in this problem. Then it says the next thing we do is multiplication and division from left to right. So I have to first do the multiplication and division. So I'm going to go until I see a times sign or divided by sign. Oh, there's a times sign right there. So I have to do this part first. So now I will get this. 8 plus 2 times 4 equals 8. So the answer to this problem is 16, because I had to do multiplication and division before I did the addition. I have to follow the rules. Let's choose another one here. Let's choose one that's something like, oh, let's do this one. 2 to the 4th power minus 8 times 2 plus 3. What does that equal? Okay, I'm going to do parentheses first. Here are my parentheses. 2 plus 3 equals 5. So now I have 2 to the 4th power minus 8 times 5. No more parentheses, so I'm going to go and do exponents. 2 to the 4th power means 2 times 2 times 2 times 2. 2 times 2 times 2 times 2 equals 16. So now I have this, 16 minus 8 times 5. Oh. Done with exponents. Now I have to do multiplication and division from left to right. So I'm going to start here and go until I see a divided by sign or a times sign. And there's a times sign. So I have to say 8 times 5. 8 times 5 is 40. Now look what I get. Now I get 16 minus 40. 16 minus 40, as you know, is a negative number. So the answer to this problem is a negative 24. Did you guess that when you looked at the problem? No, because you had to follow the order of operations to get the correct answer. That's how you do order of operations, or PEMDAS. Parentheses, exponents, multiplication and division, addition and subtraction. Easy.
Easy peasy, so he says. I'm just, all right, I want to talk about percentages. Okay, we just talked about the order of operations. We use percentages. It's actually part of the permit variable. I mean, why do I keep saying variable? Value, permit value. As far as compliance, I just spent all day today talking about regulatory updates and issues and compliance. There are some updates. It doesn't really apply to PVSC or Jersey City, but we actually had an interesting discussion as far as combined sewer overflows, which is an issue to Jersey City and PVSC. But at any rate, if you're going to look into the NJPTEs, as I guess that's the best way to pronounce it, there are certain base parameters for permit compliance. One of them is what's called percent removal or percent efficiency. I went over the formulas on the ABC sheet, but the permit compliance for TSS and BOD, TSS means total suspended solids, BOD means biochemical oxygen demand. PSS is just as it implied. It's a measurement of the solids that's going to go into the receiving water. BOD, a little bit, well, it's not difficult to explain, but it is a value that measures the strength of the pollution in the water. If that material that's in the water has a high BOD when it goes into the receiving water, the microbial life inside that receiving water is going to say, yeah, we got food, baby. And they may consume that food and reproduce to the point where they deplete the oxygen in the waterway. That's a measurement called BOD. It's a 5-day test, 20 degrees Celsius in the dark, with usually a seeded sample, depending upon where you're taking it from. But you measure the dissolved oxygen initially, then you measure the dissolved oxygen after 5 days. When we go to do the sampling stuff, I'm going to kind of get into that a little bit deeper as far as the certain parameters. There are a lot of hoops to jump through with the BOD test. But it's a 5-day test, and the accepted, usually the permit is 85% removal. If your plant goes below 85% removal, you ring a bell in Trenton, and they get paid. In other words, you have violated, and you have to pay a fine. Well, usually it depends how well the letter is written, because sometimes there's such a thing as what's called an affirmative defense. And sometimes they say okay, sometimes they say not, but enforcement is something that takes place. You have to abide by the permit. So we use percentage, and it's just what it says here. It's another way of writing a fraction or a decimal. It is thought as parts per 100. In other words, 85%, if you were to take that and write it as a fraction, it would be the same as 85 over 100. If you wrote it as a decimal, it would be 0.85. Essentially, you just move the decimal place over 2 places to the left. Because the initial number is per 100, you want to make it so that it's not per 100 and it becomes a decimal. That's important to remember when you're doing certain calculations. You're going to be writing percentages, not as percentages, but as decimals. So if you're going from a percentage, if you're given a percentage and you have to write it as a decimal, you move the decimal place over 2 places. Each decimal place is 10. Right, so it's 10, 100, 1,000, 10,000, 100,000, a million. That kind of goes along with when we get into what are called logarithms. All right, which is base 10, 10 to the 1 is 10, 10 to the 2 is 100, 10 to the 3 is 1,000, 10 to the 4 is 10,000, 10 to the 5 is 100,000, 10 to the 6 is a million. But with percentage, it's a part per 100. Now, a lot of times we work in parts per million, which is milligrams per liter. We'll get into that, but I'm talking about percentage. All right, now we all do percentages. I know every one of you do percentages. Every time you go out to a restaurant and you give the server a tip, it's usually based on what, 20%? Or, well, I don't know. I always try to give a little bit more than 20%, but that's kind of like the rule. It used to be 15%, and then I guess as years went on, we realized that servers don't make a whole lot of money on an hourly basis, so they kind of work for their tips. So 20%, right? So if your bill is $100, you do this. I know everybody does it because you do it. If your bill is $100 and you want to leave them 20%, you leave them 20 bucks. That's 20% of 100. Okay. And like in this one, if you have $1, if you move the decimal place, that dollar becomes 100. If you have a quarter in your pocket, that becomes 0.25. That's 4 quarters make $1. All right, so 25 parts per 100 is more easily recognized as 25 of 100. So that's a quarter to $1. All right. But percentage is based on 100. Now, again, like with this damage, this thing here, 0.25 is the same as 25% if you write it as a percentage. Remember, if you go into a percentage to a decimal, you move the decimal place over 2 places to the left. If you're making the decimal a percentage, You go 2 decimal places to the right. Every decimal place is a power of 10. Okay. Now, what I've got a little sheet with certain percentage problems. All of these are the same. It's taking the percentage of something. Now, when you're doing, say you're doing a chemical calculation, right? Say you have to add whatever. You don't know what you have to add as far as a percentage of a dry chemical. Well, dry chemicals usually already soluted, you make it down, but anyway, say you have, like, I'll give a great example, hypochlorite, sodium hypochlorite, very common, used in a lot of the business, right? The expectation for available chlorine for hypochlorite is 0.12 or 12%. So if you were to calculate, if you wanted to get the pounds of chlorine, right, that you were using, 12% available chlorine, whatever it is, we'll call it sodium hypochlorite because that's probably the most common. Say 12%, it's available chlorine. You would do the pounds formula, and I'll do it later, but we're going to have milligrams per liter times 8.34 times mgd. So you'll have what your known dosage is that you get. The lab says, hey, you should feed this much to the water. Okay, fine. And if you do that, milligrams per liter times 8.34 times mgd, that's going to give you the pounds of pure chemical, or the pounds of chlorine that you would be adding to that water. Now, of course, pounds don't mean anything to us, especially if it's a liquid chemical. You have to convert it to gallons, but you do that part. But now you got to account for the fact that there's only 12% chlorine in that water. So you divide that number by 12 as a decimal, 0.12. So if you're using the pure chemical, you would do milligrams per liter times 8.34 times mgd, and that's going to give you the pounds of whatever that chemical is. But if there's a concentration of the actual chemical that you're going to use to work in that solution, you have to divide it by the percentage as a decimal. Percentage. Now, the problems that I have here, not that they're easy, but it's taking what is the percentage of this, what is the percentage of that. So basically, you're going to be multiplying everything by the percentage as a decimal. And like I just did the first one, 25% of 100 is 25. Now, if you were to do that as a problem, it would be 0.25 times 100. And if you do that on your trusty, rusty calculator, that's what it's going to look like. 0.25 times 100. It's going to come out as 25. You write the decimal, you write the percentage as a decimal. And just for a clarification, I just want to throw this up here for a minute. I'm not saying you have to have my calculator, because everybody's calculators are a little bit different. But I can say, like, the one, I think you guys can see it. I don't know. Let me go off of this for a minute. So, oh, I see. This is what I'll do. So I'm nice and big. There you go. See, I use this. This was cheap. It wasn't really a big deal. Texas Instruments. This is a scientific calculator, but it was fairly cheap. No big deal. It wasn't like a huge expense. Not like, I don't know if some of you had calculus in school or something like that, or you had to do quadratic equations, or maybe if you did take heavy duty math in high school or college, many times they ask you to get a graphing calculator. I know when my kids were in public school here, I can't remember what class it was, but they actually gave them. I bought my son a graphing calculator. He said, Dad, they gave it to us at the school. But these are cheapos. These are not that expensive. Texas Instruments, maybe it was 10 bucks, 12 bucks in Staples. You know, solar powered. The first one I had before it crapped out, I think I dropped it, or I put it in a bag, and it got crushed. It lasted me more than 20 years. So, but it's something that you guys should have. Now, yeah, everybody's got a phone and their calculators on their phone. We know that too. Nothing wrong with that, at least not for this class. It doesn't, for me, it doesn't You know, it doesn't matter to me. If it doesn't matter to you, it doesn't matter to me. However, however they're going to slice up the state exam, this is a no-no. When it was in person, this was a no-no. And I don't know if they're making testing centers available because some people can't stand logging in and doing the test remotely. But you can't use a phone. What did I do? You can't use a phone. For the class, I don't care. Everybody's got a calculator on their phone, and I think pretty much everything's on our phones, right? You have, see, here's my little calculator on the phone. And I have used it, but I've gotten used to using my trusty, rusty, dusty old calculator because when I was taking exams and when I was going through my licensing process, I knew that if you had a cell phone and you went into the state exam, they'd throw you out. They wouldn't let you take the exam. And I keep shaking this. I keep turning the light on. I don't even know how I'm doing that, but I'm doing it. So let me do this. Shut this off. So that being said, it's maybe a good idea to invest in a little calculator. It doesn't cost much. Again, this one is a scientific calculator. What's interesting, they always come with those little papers in the back where it explains different things that the calculator has as features, and it actually shows you how to do some things. Don't be stupid like me. I lost mine. You can always get it online because there are certain calculations. You look at all them buttons, it's like, I don't know how to use them. But it's a good idea to learn how to use them. Get used to using your calculator. You can play with it, you know. I know for geometric mean, you can do it on a calculator. But when we do geometric mean here, it's not going to be in, actually, I think it's going to be in the chlorine or the bacterial section. I'm not sure. But I have a geometric mean problem. But I'll show you a trick that Joe Bones taught me. And if you don't know who Joe Bones is, you probably don't. He's kind of like the elder godfather of wastewater treatment in the state of New Jersey. Joe Bonacorso. He actually worked for PVSC for a time. And then he went to work for Joint Meeting. Now he's retired. I think he's the licensed operator. There's a little plant up in Berkeley Heights because I think he's still doing that because he arranged a tour for one of the previous classes there. But he's like the elder statesman of wastewater. He's really smart, really brilliant. And I'll show you what he showed me. It's him, not me. But anyway, let's go back to the share screen. So let me shut my camera off. Oof. All right, so we're going to talk about percentages, and then I'm going to go on the board, and I have some problems. I'll put the problems up, and then maybe I'll write them on the board, and then I'll do them on the board. You guys can help me see how it's done. So what the problems that I'm going to do are all going to be multiplication, not that tough to deal with. Think about it if you're calculating the tip for a server. And here we go. There we are. Boom. All right, so these are these. And some of these you don't even have to think about it, that you can do. So we have 10% of 100. I kind of said that already. All right, 10%. It would be 0.10 times 100. So if you take out your rusty dusty calculator or use your phone and you tap in decimal place 0.10 times 100, you're going to come up with 10. All right, so let me put my camera on. I'll take off the share screen and I'll write these things on behind me and maybe we can do them together. Now I need to clarify this. I put view active camera, and it's not because I'm like real vain or anything, but to see the board, I need to do that. And it would be, cool if you guys don't flip your cameras on, because then people aren't going to see what's on the board. And I'm not 100% sure of what you guys are seeing. I think you're seeing it. Maybe give me a minute. I'm going to log into the class as an outsider so I could see what you guys are seeing. So you're going to see me pop into the class. Or maybe you won't see me pop into the class. join. I'm joining the class. I'm going to join the class like you guys. Okay, cool. So now I'm seeing what you're seeing, and you guys can see the board. And it's interesting because you see those black lines that are doing. That's because at one time, however it was working, people weren't seeing the board, and I made borders. All right, and hopefully the lighting stays lit. We got to stay lit. I'm assuming that you guys can see the top and the sides, and but this shouldn't take long. Let me do this. This side looks a little cleaner. Here we are. Put it on the back side. Flip that. All right, so like it says on that little paper, I don't want to get too much of the glare. All right, and I need to remind myself of what I wrote. So I'm going to write these down here, right? So let's do 10% of 100. And then over here, it's going to equal something. Over here, we'll get 15% of what? Of 250. I don't know if this board's too small. Okay, 10% of 100. So this one is, it's going to be, you're doing it this way. Make believe the of is a multiplication sign, so you get 10. All right, that one's not too, we do this. All right, and then say you go out with your friends, and maybe the waitress isn't the best waitress in the world, or waiter, and you don't want to give the waiter 20%. So 15% of 250. All right, and if you do it, it would be 0.15 multiplied by 250. That's how you do it on a calculator. I always write decimal places. I always write zeros in front of my decimal places. Not everybody does that. And if that bothers you, I apologize, but I do that. I've always done it. Doesn't mean you have to do it. I know there was a fellow in the class a couple of years back. He was a machinist and he hated it. I don't know if it was specifically because he was a machinist. He hated that I put zeros in front of decimal places. It's just a habit that I've picked up. For 0.15 times 250, do it on a calculator, it's going to be equal to 37.5, right? 37.5. All right. The next one, Mark 3, is 17% of $1.380. 350, right? Again, that's the same thing. This is per 100. Same thing as 17 over 100, or moving that decimal place to the left twice. The of means 350. The of means multiplication. And the answer for that is 59.5. Right? Not too shabby. All right. The next one, and what's the next one? Same thing, 12% of 240. Maybe you didn't like the waitress, you only wanted, or the waiter, and you only wanted to give them 12% of the tip. All right, so because they were lousy, maybe the food came cold, they were rude, so you only want to give them 12%. So 0.12 times 240 is 28.8. Okay. So they're mad at you. They're chasing you out the door. You cheapskate. How dare you only give me a 12% tip, right? All right, 28.8. And the next one, now this waiter was terrible, but you feel obligated to give them something, but you're only giving them 1%. Is it 220? No, it's 200. It's 200. 1% is 200. right? You don't even want to get on this, but people you're out with, oh, you got to give them a tip. So remember, 2 decimal places to the left. So it would be 0, because I always put a decimal place in front of I always put a 0 in front of my decimal places. You don't have to, but 0, 1. Now you can solve this for yourselves by just going on a calculator and you put 1 divided by 10. And then a trick, because this is 1%, you can do this with 10% too. Again, it's multiplied, but you can move the decimal place over, right? 10%, 100%, or in reverse, boom, boom. That's 1%. 0.01 times 200 is 2. So you left this waiter a $2 tip. How cheap are you? How cheap are you? All right. So I think you guys, hopefully you guys get the gist of this. And this is if you want the percentage of a value that you already have. So 1% of 200 is 2. I'll do one more and then I'll let you guys. Oh yeah, no, that's right. So let's try. You really like this server. This first server was wonderful. It was the best server you ever had, and you're feeling really generous. So you want to give them a huge tip. 90%. That's big, right? You want to be a real big shot, you know? So that's 0.9 times 185. And if you do that arithmetic, it's 166.5. So that's the tip, right? That's the tip. You have one happy server. He's a happy, or she's a happy, or whatever they are, somewhere in between today. They got a happy server. You gave them a 90% tip. Okay. So hopefully that kind of gets you the gist of how to do these. These are not too bad. Now, on the next page, we're going to do something else. And I'm going to talk about this, which looks ridiculous, but it makes sense when I tell you, when I explain it. But I'm going to go back to the presentation and it's time for a little feedback. So I'll let you guys give me some answers for the other ones. But we are going to mention this. We're going to talk about this in minus out over in the next set of problems. And then we're going to, the next couple of them, we're going to have some percentages. Actually, there's one here that's a ratio. But anyway, let's go back to this. And I'll shut my camera off for a little bit. Okay, so which ones did I do? I did up to 6. I did 90% of 185. So that's your turn. What's 27% of 350? You can either call out or you can send me little chat messages. 0.27 times 350 is what?
$94.
Beautiful. Well, yeah, 94.5. But yes, that's cool. Good enough. We do work for the government. Sometimes you're going to hear me say they're good enough for government work. 3% of 990. I am going to mention rules of rounding a little bit too. 3% of 990. And I know this may seem elementary, but we got to kind of take baby steps. The next page is going to be a little bit more intense. 29. And I mentioned this. Don't forget
29.7.
Right, yeah, don't forget about decimal places because they do mean something. Now, the whole significant number thing is important. If well, I have one problem that I'm going to share with you guys later on down the road. It's in the disinfection section. I could tell you the rules of rounding don't matter. If you're buying a commodity and your numbers are in the middle, beautiful, thank you, Christian. If you're buying a commodity and the numbers are in the middle, if you round it down, you're not going to have enough. If you round it up, you'll have enough. The normal rules of rounding for our thing is if it's 0 to 4. Like say you have 23.76, and the answers that you're asked to give has 3 decimal places. 23.76 would really mean that you would round up to 0.8, 23.8. And it depends on how far out the answer is going to be, where you're looking as far as your answers are concerned. Here, I have to, somebody's got their camera on and I just want to, I can't shut it off. Oh, could you shut your camera off? Because, is that Ron? Just do me that favor. Thank you. Because I want everybody to be, I want to, you know, don't take offense. You're a handsome guy, but yeah, don't forget about the decimal places because they do matter sometimes. Years ago, as far as there was a compliance issue with the RAB, and it was a matter of decimal places. And I can't remember all of the details, but we had all of the windbreakers down there. We were doing a test on the RAB, and windbreakers, when you see windbreakers with guys with ties, that's usually the EP compliance. It's just where the lawyers start jumping in, the enforcement people. And there was an issue with a parameter on the RAB, and it was a matter of decimal places because the permit said one thing, and then there was an extra decimal place in the readings, and it's like, well, you're not in compliance. It's like, yeah, but the rules of rounding say we have to round up to the next number. I didn't really get specifically involved, but I know there was a controversy because of decimal places, believe it or not. I think it had to do with the volatile VOC's reduction of the RAB. It all got worked out. PVC didn't pay any fines, but it was during a big RAB test. They do them every once in a while. Anyway, where did we leave off? We left off at 3% of 990, said 29.7. Next one is 25% of 100. Should 25. Be 25. That's an easy one. 33% of 66. Again, 0.33 times 66.
21.78.
Beautiful. Thank you. 5% of 250.
12.5.
12.5. 7% of 1,000 is
70.
70. 10% of 3,500,000. That's just usually when you have 10%, you can just slip the decimal.
Isn't, yeah.
350,000, right? And 80% of 54,000 is one more. Well, I'll tell you, it's 43,200. All right, so the next page is going to address a couple of things. The next page is going to address a couple of things. I'm going to kind of do these one at a time. The bottom gets cut off. All right, so I'm going to read through these problems, and this is part of the first quote-unquote problems that we deal with. And remember what I wrote behind me up here on the board. N minus out over N times 100. Okay, so we'll read the first problem, and then I'm going to do it on the board. And that's an important function when you're doing these problems, to read the problem. Read the problem, extract out the numbers, that whether you're going to use them or not, and then you can figure out whether you're going to use them or not, and then do the calculations based on what you know and come up with the answer. But it's important to read the problem fully. So this question reads, an activated sludge wastewater treatment plant has a daily flow of 25 mgd on Monday. All right, so it's talking about MGD stands for million gallons per day. In case you didn't know that, that's what it stands for, MGD. Okay, on Monday. The influent TSS is 200. Influent, that's what's coming in. Influent, I substitute gazinta. The influent is the gazinta. The effluent is the gazala. Stuff coming in is the influent. The stuff leaving is the effluent. All right. As far as a plant's concerned, especially for this particular parameter, TSS stands for total suspended solids. And this number is not outrageous. This is a fairly realistic number within the range that you would expect. If you had 200 milligrams per liter of total suspended solids in the influent of the plant, that wouldn't be a surprise. You know, that's kind of within the working range that you would expect. Of course, depending upon your plant, the conditions of the collection system, how much water is coming through the plant, storm water, whatever. 200 is not out of the realm of reality, which is kind of why I picked this problem. The effluent is 15 milligrams per liter. And again, that's not outrageous either. Of course, it depends upon the permit of the plant and what the numbers are. I'm going to talk about something called the 30-30 rule, which comes into play. It's kind of a base, we'll call it the basic permit. Plants do have different parameters that they have to put out based on the waterways that they're putting it out to. Certain waterways are a little more sensitive. And if a wastewater treatment plant has to discharge, their permits are going to be a lot more stringent. Usually, of course, they brought it up today. In New Jersey, every freshwater discharge is considered a potential drinking water source. I had said, and I don't know if I said it to you guys, but that there are certain plants that have more stringent regulations because of where they discharge to. Like the Passaic River is a known water source. It's a known drinking water source. And that's why some of those plants that distribute into the Passaic River or tributaries to the Passaic River on the freshwater side, they have very strict nutrient, just specifically nutrient limits. One of those nutrient limits is nitrate. Nitrate is 20 milligrams per liter causes problems. Did I say 20? 10 milligrams per liter is the MCL for nitrate. If a water treatment plant has higher than 10 milligrams per liter of nitrate on their intake, that could cause a problem for people drinking that water. So the wastewater plants upstream have to make sure that they don't come anywhere near that. There can't be 10 milligrams per liter of nitrate in the intake of a water treatment plant. It develops this thing called blue baby syndrome, where especially in babies who are sensitive, the oxygen can't get into their blood, and they literally turn blue. It's a terrible, terrible thing. So nitrate is it's a primary contaminant, primary contaminant with a limit, and the limit is 10 milligrams per liter. So this problem, and then actually I went off the reservation. This is talking about total suspended solids. So an activated sludge wastewater treatment plant has a daily flow of 25 million gallons per day on Monday. The influent TSS, that's the water coming in. It's usually measured at the headworks or coming into the primaries, is before any treatment takes place, is 200 milligrams per liter. The effluent, which is the water leaving the plant, is 15. And it says, what is the percent removal of a TSS for this plane? That's the problem. Okay. Let me just put up my camera. And what I'm going to do is I'm going to do it on the board behind me. Well, wait a minute. Wait a minute. Does that work? I'm looking at it with my camera on. Can I put them both there? I'm about the same size, right? I don't know how it looks to you guys at home, but on the phone, it looks like it's about the same size. It does make it really small. But this back here, this in my without over in is what I'm going to use. I'll just take it off the share screen. All right. Groovy. I just didn't want to be too much of a distraction. So this is what you're going to use. In or influent minus out or effluent, and you divide it by the influent and you multiply it by 100. When you're trying to yield to a percentage and you're doing a calculation, guess what? You multiply by 100 so that it will be in percentage. If you don't, you just get a decimal. And I mean, if you're sharp enough, it doesn't matter because it's just going to be that way, if you understand that. So what I like to do with these problems, I'm going to show you what I like to do. And again, you don't like to do it, that's fine. I have found that many people put their own things on things and they're figuring out just fine. But I don't do it with every problem. A couple of things that can be helpful. Drawing pictures and pulling out the values. All right, so what I'm going to do with this one is I'm going to pull out the value. So I have a little column here called known. Right, and I'm going to put the values that are in the problem. So we'll read it again. An activated sludge wastewater treatment plant has a daily flow of 25 mgd. So I'm going to put that in there. And then I got to figure out what I'm going to use it for, if I'm going to use it. That's a little hint, if I'm going to use it. And then it has, what's next? 200 milligrams per liter, the influent. And I'm just going to put influent. And that's 200 in the form of 200 milligrams per liter. 200. And then the effluent is what? 15 milligrams per liter. And then the unknown is what I'm going to try and figure out is the percent removal, also known as efficiency. Percent removal. So, I mean, I remember the formula because it's tattooed in my brain. You guys might not know that, and you could probably look it up on that ABC sheet. I don't have to, so I'm gonna write the formula out here, and I like write it this way. You could put influent, effluent over influent times 100%, and that's going to get you the percent removal. Remember, influent is what's coming in, effluent is what's going out. Now, this little subtraction sign tells me something. You are getting the difference between the influent and the effluent. So you are getting what was pulled out, and you're going to divide that by the influent. Okay, now in this formula, there's no place for a flow. It doesn't talk about flow. It's not in there, so we don't need the flow. It's strictly a concentration. Now, most of the numbers that we receive from the lab are going to be in milligrams per liter. It's the same thing as parts per million. Just like a percentage is a part per 100, milligrams per liter is a parts per million. Okay, now there is a way to do that, and I'm going to show you guys that later when we do the pounds formula. But for now, just remember, milligrams per liter is a parts per million. That's what it means. Just like a percentage is a parts per 100. So we take our 200, right? We take what the gazinta is, and we subtract it from the gazouta. This is both milligrams per liter. And then we divide that by the Gazinta, and then we're going to multiply it by 100%. Okay, now, first things first. You work from left to right, but you're working on the top and the bottom. You're going to take 200 and subtract 15, which I believe is 185. Then you're going to divide that 185, because that's what this line means basically, is divide. 185, and you're going to divide it by 200. You're going to get a decimal. One, because the numerator is lower than the denominator, so you know it's going to be less than 1. I believe you get what do you get?
925, 0.925.
0.925. Now, let me look here. All right, 0.925. And then you multiply that by 100, and it becomes 92.5%. Now, if you look at the answer choices, and I'll go back to that one, we'll look at the answer choices. Look at the answer choices. If 93 was there, we might consider that to be the answer. Why? Because it's 0.5. Right, 0 to 4, you leave it alone. 5 to 9, you round up, depending upon the amount of significant numbers that you're looking for. But 93 is not there as a choice. So it's 92%. That's the answer, 92%. All right, now the next problem, all right, and that's how you do the in minus out over the n, or percent removal. Not that much. And when I talk in percentages, I got to remember that it's per 100. Groovy. All right, cool. Thank you, guys. Appreciate your participation. Some of the guys were sending me answers through chat messages, and that's nice. Thank you. Appreciate it. That's interesting. In the next problem, I kind of switch gears on y'all, and maybe that's not fair, but I want to illustrate a point. And again, this is somewhat what you would consider as a real life scenario, sort of real life scenario. How come the screen is not there? Let's see. Let's go back. Let's go back. Actually, I got to make it small. Why is this coming up? Wait a minute. Sorry, folks. I accidentally took it off the screen, so I see what you're seeing and you're not seeing anything. All right, cool. Okay, so in order to, because it cuts off at the bottom, I'm going to try to blow this up just a bit. Man, that ain't going to work either. All right, let's try to do it slowly. All right. Now you're looking at the next one and you're saying, what the heck is that? That's not a percentage. It's illustrating something else, and I'll talk about it in a minute. Now, some of you work with pump speeds. I'm sure you do, especially if it's, say, a progressive cavity pump, what was called a positive displacement pump, especially a metering pump. Okay. Now, this doesn't illustrate that to a degree. It doesn't give you a flow, but you can look at this problem as a flow problem. But it's basically a ratio. Now, if some of you remember ratios, now it does have percentages in it, so that's why I decided to use it. So this says, and actually you don't have to do math to do this one. So, and then let's put it in the mindset of a flow, just because you're making it easier, right? And I'll add some words to the problem, but it says if 157 is 37.4%, what is 74%? Now let's add some of our own thoughts to this problem.
If 157 gallons per minute is 37.4% of the pump speed, what is 74% of the pump speed? That puts it into a little bit different light. They're not adding words there, but you can do it that way. And then I'll show you how to mathematically do it. All right. So what it is at 37.4%, whatever it is, gallons per minute, liters per minute, pounds per minute, is 157. And say you increase that to 74%. What's the value going to be? Do you even need to do math to do it?
It'd be D.
D, yeah, it would be. All the other ones are less, right? So you don't even have to do math to this one. This is a quickie. This is like a 5-minute problem, if that. If that light bulb opens up to you, where it goes on in your head, because that's how I always address this problem. Now, if you have 3 values, 2 of them being the same that you know of, basically it would be 3 different values, 2 being the same, and 1, this particular problem, you don't know what the value is, and you're asked to find a 4th value that is equivalent to that 3rd value that you don't know what it is, you could set this up as what's called a ratio. Okay, and it's the same thing. It's as if 157 is 37.4, so what would it be at 74? So you're trying to find whatever 157 is, whether it's pounds or gallons or liters or whatever it is, you're trying to find the same thing of that, but this machine now is running at 74% of its capacity rather than 37.4. And you're absolutely right, it's D. No math involved, but I'm still going to write it on the board just to kind of illustrate that and show you guys a little bit. And this is what's called a ratio. Now, this is the way I do these things. And it's like an equivalency. So I put an equal sign between the two, because essentially that's what it is. It's almost like you're creating a fraction. There I go. Right, so at the same time, let me just flip this sucker over. Got new markers for this class. So, you could pull it out and do your old knowns and unknowns if you want. Right? And the knowns are, what are the knowns? Whatever it is, they don't tell you, is equivalent to 37.4%. And then we don't know what it is at 74%. We don't know what the value is at 74%, although we already did, because you don't have to use math to do this. A quick way to do this, if 157 is 37.4%, in proportion to that, or a ratio to that, what's 74%? And yeah, I know our math teachers used to like X, but I don't like X. I'll put a little question mark. The quick way to do this is to say that's the same as 174 multiplied by 74, and then you divide it by 37.4. You say, whoa, what did you just do? When there's an equal sign, right, that means both sides essentially are equal. What you do to one side, you got to do to the other. Now, if you wanted to play games with algebra, this is no place for you. You would multiply both sides by 74. This sides cancel out. You put that one by itself. So this becomes 74 times 157 divided by 37.4. If you do that arithmetic, you should get 310. But you already did it because you told me what the answer is. Now, when I set up a ratio, I always do it this way. I put the unknown on the right-hand side in the numerator. I don't know why. That's just me. It always works out that way. That's how I do that. Very helpful.
Does it matter if you put it on the numerator or the denominator?
I think it does change some things. I never really did it. I always did it that way.
Okay.
I mean, if you want to flip it around and see what it does, I'm here. But whatever you do on one side, you got to do on the other. So let's see if it comes out differently. That's the way I've always done it. So let's write it this way. We'll see if it comes out the same, because honestly, I don't know. So let's flip it around. So 74% is 157. No, 37%. It might not come out the same, which is why I probably do it this way every time. And then, so what is 74%? You just got to take extra steps. But let's see. So this is multiply both sides by 157. This goes away. Changes the equation. 37.4 equals 74.157 divided by something. Now you can multiply each side by something, but you're still going to be stuck with this. You got to do extra steps. That's why I always do.
Okay.
You can. It's just going to take you extra steps. Because you want to get what you're solving by itself. So you basically have to say, do this, and then do this. These go away. Then you're left with question mark multiplied by 37.4 equals whatever 74 times 157 is. And then you have to divide both sides by 37.4. And then I don't really know if it comes out to be the same. But while we're here, let's see. It's extra steps. That's why I never do it that way. So what is 74 times 54? Stop. $11.10. So that's $11.10. And then you divide that by 37.4. Doesn't come out the same. It does not. It's better to always put the value of what you're trying to, what you don't know up in the right-hand side. It's not going to work out the same. I don't know why it doesn't work out the same, but it doesn't. I probably messed up somewhere along the line. Now I have a third one. And these, actually the next two, I believe, are both water problems. And if you do it wrong, the wrong answer is there. So I'm going to read it to you. And then I'm going to go ahead and I'm going to do it. Do it. To it. All right. There's 27 of this in here. Groovy. All right. Let's go down here. I'm going to be a blank page. Okay, let's try this. All right, let's do this next one. The next two are actually water problems. Now, they are, one is, well, they're not complicated, but you got to do some things. And you're going to run into that with some of these problems. You're going to have to do some things. I said it before where you have to get the units to agree. You're going to have to get things to be the same. And it's easier with the metric system. That I will say, it's easier with the metric system. But let's read it. And a lot of people make the same mistake with this problem. And I will explain. So it says if 62 grams of lime are dissolved into 1.75 liters of water, what is the percent strength of the lime solution? I'll read it again. If 62 grams of lime are dissolved in 1.75 liters of water, what is the percent strength of the lime solution? Right, a few things, and then the choices are 3.4% lime solution, 3.5% lime solution, 34% lime solution, 35% lime solution. So the answer, whatever answer it's going to be, is going to be close to the wrong answer. And you could get messed up with a decimal place. They're telling you that in the answer choices. And you could very easily get the wrong answer by missing something in this problem. But you have to address this, and this happens a lot. We have grams and we have liters. Okay, we have grams and we have liters. And actually the one below it has a similar issue where you have pounds and you have gallons. But there are conversions for that. All right, so in the first one it says if 62 grams of lime are dissolved in 1.75 liters of water, what is the percent strength of the solution? Does anybody work with lime right now? Anybody in the class? No, Adam, no. Because I'm thinking PVSE, they put that to bed in the 90s. That lime nightmare that we had down there. I don't know if, what do you, Kendall up in Passaic Valley Water, what do you use to add alkalinity to the water? Do you use lime or soda ash?
I'm not sure what they use. I'm not in that department. I'm in distribution, not in treatment.
Oh, okay. So you're not sure. Okay. No, because usually, and it's a lot more prevalent in water plants. In order to adjust alkalinity, they're going to add something to it. Lime is cheap. Lime has its own set of issues where it manufactures solids, it manufactures sludge. For lime soda ash softening, you're adding it to precipitate out calcium and magnesium hardness in water. In wastewater, a lot of times sludge conditioning uses lime. If a plant has to, say, nitrify, which is converting ammonia to nitrate, you have to usually add some form of alkalinity to the water because you need to have about 100 milligrams per liter of alkalinity in the water in order to maintain nitrification. You need to have alkalinity in the water. I'm trying to think. 7 pounds. Oh, shoot. Yeah, for every pound of ammonia that you reduce in a nitrification plant, 7 pounds of alkalinity that you have to have, that you're going to lose also. So you have to add, if there's not a lot of alkalinity in the water, you have to add alkalinity to it. It makes the water corrosive, makes it, not the alkalinity doesn't, the lack of alkalinity. Well, one, you can stop nitrification. The microorganisms that do the nitrification part, they enjoy alkalinity. They enjoy it in the water. It makes the pH more stable. It keeps the pH at a level where they can get happy. In water treatment, you're adding lime many times to add alkalinity to the water to prevent the coagulant from driving the pH down. It's a buffer. You know, some places will use soda ash, some places will use soda hydro. Soda ash is sodium carbonate. Soda ash is a powdered chemical as well. Lime is pretty cheap, calcium hydroxide or calcium oxide, depending upon the type of lime that you're going to add. That's added to the water, but it makes sludge sometimes. So you have to be careful when you're mixing and you're making a solution. You want to have as much of it dissolved because you don't want sludge in drinking water, right? So usually there's some kind of a precipitation or settling process. But you add alkalinity to the water, and that's what the main purpose is. In sludge conditioning, if you're adding a base like lime to the water to bring the pH up, a high base will actually disinfect the sludge too. That's used many times as quicklime. Calcium oxide is used in sludge conditioning because it actually heats up the sludge. It jacks the pH up to about 12. It heats up the sludge, and it actually helps to condition the sludge to somewhat sterilize it. It will make a Class A product. NCUA, they add lime to the sludge. I don't think they have to because they have a heat treatment process there. They have a sludge drying process, which also sterilizes the sludge. But this was part of their permit. I guess but they literally pasteurize the sludge. They heat it up and let it sit in a tank and stay warm for a while. But anyway, lime calculations are like this. So here we go. We got 62 grams of lime that are dissolved into 1.7 liters of water. And you say, well, you got grams and you got liters. You got to bring the two together. You have to make them both the same in order to make the problem work. In the one below, you got to do the same thing, but it's between pounds and gallons. Same problem. You got two different things. Now, the fact that these problems are in percentage tells you that you got to multiply by 100. Okay, well, we got that one answered, but we still haven't figured out how do we do this problem. So you can either convert the grams of lime to a volume in liters, which isn't really practical because it's a powdered chemical, or you convert the liters of water into a volume by weight or mass, because that is more practical. There's a direct equivalency, and this is the beauty of the metric system. Liters and grams go together very nicely, at least with water they do. The weight of water and the weight in grams of water, the weight of water and the volume of water are very similar. The numbers are pretty close. And that's what I'm going to go over. So I'll read it again. I'm going to do it over here. So we got 62 grams of lime. And you're dissolving that into the water. That's usually a mixing tank. You're putting a little bit of this lime in the water and you drink it all up. No, that's the coconut. No, that's a song. All right, well, you put a little lime powder, and you mix it nicely, and you hydrate that lime, and you let it mix, and you let it mix. And this is not that much, so it's probably not going to form a whole lot of sludge. And the purpose of this is to add alkalinity to the water, usually to adjust the pH, to maintain that. Because you add a little bit more. Now, it's only 1 liter of water, so this is making a solution that you're going to be adding to the bigger picture, so to speak. So for every 62 grams of lime, you use 1.75 liters of water to what they call flake it. You know, mix the water and you make it like a cake dough. Now, if it was a larger plant, you wouldn't really even see that sludge. But this makes it so that when it's added to the water slowly, it'll do something to the water, it'll add its alkalinity. If you add more of it, you're going to get calcium and magnesium precipitating out in the water, which may be a good thing if you have high hardness, like 150, 200 milligrams per liter of calcium carbonate in the water. So this is all groovy, right? But you got to get the units to agree. And we're going to do that with a lot of problems. You got to get the units to get together. You got to get them to agree. So the first thing we got in the answers, we got percentages. So somewhere in this solving of this tremendous problem, you're going to multiply by 100 to turn it into a percentage. Now you got to figure out Okay, 62 grams of lime dissolved into 1.75 liters of water. You've got to convert the water, the weight, the volume of water to mass of water or weight. Then you have to figure out what I'm going to figure out. Okay, so we're going to do all that stuff. All right, well, I can tell you that a liter of water weighs a kilogram, which is the same thing as what? 1,000 grams. That's an easy one. Okay. 1 liter of water weighs a kilogram, which is the same as 1,000 grams. And if you were thinking about it in parts per million, it would be the same as a million milligrams. There's that milligrams. Ooh, see? Okay, so a milligram, all right, there's that part of that million, right? 1 liter of water weighs is 1,000 grams. 1,000 grams. 1 liter of water weighs 1,000 grams, which is the same thing as a kilogram, which is the same thing as a million milligrams. So there's your milligrams per liter, parts per million right there. Okay, but anyway, that's part of the problem. That's what you got to figure out. Not part of the problem, part of the solution. So you be the solution. You don't be the problem, you be the solution. All right, so let's put this up on the board and we'll do it for y'all. You guys probably already got it because I've been bloviating about this problem now for about 10 minutes. Let's see. Yeah, I'm seeing what you're saying. So that's why I'm looking down. I want to make sure that, because I've had it happen when for some reason I've locked up and I didn't realize it. So that's why I'm in the class twice. So let's go for unknowns and our unknowns, just for ha-has. 62 grams. 62 grams of what? Lime. You put the lime in the coconut, you drink it all up. Yeah, that's a song. Calcium. Oh, I can't remember the chemical symbol for calcium oxide. I think it's just CaO. Not sure. You just can look that up. All right, so 62 grams of lime. And 1.75 liters of water, which is H2O. 2 parts hydrogen, 1 part oxygen. And our unknown is the percent of solution, or yeah, I forgot the chemical symbol for calcium oxide. I think that's it. Somebody wants to look it up and let me know. I'm here. I'm here. I'm here. All right, so what do we got to do to solve this problem? We're looking for the percent solution. So we know that somewhere in this equation, we're going to multiply by 100. Because that's going to be, it's going to be a percentage. But we got to figure out something. So I'm just going to kind of write it out and then I'll fill in the numbers later. So it's the weight of lime. All right, that's the weight of lime. Over, and this is where people mess up. The weight of lime multiplied by the weight of water. Did you catch that? All right. First of all, I've already determined we got to get everything as the weight. Weight. You got to get the weight. So it's the weight of the lime divided into the weight of the lime multiplied by, oh no, I'm sorry, not multiplied. Did I put multiplied? No. Added to the weight of the water. Many people just say, oh, it's the weight of the lime over the weight of the water. No, it's the lime solution. So you have to account for both the lime and the water on the bottom. And we know we got 62 grams, so we can fill them blanks in right away. We got them. That's easy peasy. 62 grams. Now we got to figure out what the weight of the water is. Now, I already said this. In case you don't know, well, now you know, excuse my back. Okay. We don't know what this is, but we can figure it out. I already said this. We have 1 point, and this is how we do conversions too. Hey, what I'm gonna do it down here. Use my back again. All right, so say we got what, 1.75 liters of water. That's what we want. That's what we have. Now, we want to convert that liters of water to grams so we can plug it in there. So you're going to be left with grams, not graham crackers, but grams as a weight. Okay, so when you do this nonsense, you want to get the same stuff opposite each other in the equation. All right, you catch that? And then it'll tell you what to do. So I already just said it, 1,000 grams equals to 1 liter of water. Right? 1,000 grams equals to 1 liter of water. Now, if you write the conversion this way, this is what you have, this is what you want. What you determine is, what do you have to do to get what you want from what you have? So you write a little conversion here. We're going to do this a lot. All right. I know 1,000 grams equals 1 liter of water. We want the liters to go away. We want them on opposite sides so we cancel them out. What's in between these two? A multiplication sign. 1.75 multiplied by 1,000 grams, and you're going to be left with grams. Capiche? So this now becomes 1,000. Oh my goodness, Coop, you got terrible writing. All right. 1,750 grams. That's the weight of that water. Obviously, the weight of water, the density of water does change, but it's pretty much accepted that 1 liter of water weighs 1,000 grams. So where does this 1,750 go? It goes right up here. Now you have all the weights are the same. So it becomes 62 grams divided into whatever 62 plus 11750 is. And I believe it's 1812. You know, like that, who was that song? No, that was, right, so it becomes 62 over 1812. Then you multiply that by 100. Where's my calculator? Right, you're doing the solution. You're incorporating that, and I'll do it right here. In 1814, we took a little, no, that was different, 1814. Beautiful, thanks, Felix. And somebody else gave me the answer too. I gotta look and catch up. Right, so when you do these kind of nonsensical problems, and you gotta get the solution, what the percentage of the lime solution is, you have to get all the units together and you include, first it's the weight of the chemical, over the weight of the chemical, add it to the weight of the water. And then because they want it in percentage, you multiply that by 100. The hitch in the giddy up here was this liters of water. And that's just something you're gonna have to remember. As a rule, as far as water goes, 1 liter of water weighs 1,000 grams, which is the same thing as a kilogram, which is the same thing as 1,000,000 milligrams, which is why milligrams per liter is a part per million, in case you're interested. So that's not too shabby. not too shabby. And I see, and please excuse my back. I know I'm walking back and forth, and I do apologize for that, but just the way this setup is actually, I kind of like the setup and where I go to teach in person. They got this big TV. All right, thanks, guys. Oh, CAO is right. Thanks, Felix. Thanks for looking that up, my friend. Thanks for looking that up. And then Jonathan, the answer is D. I'm sorry, I'm catching up to the messages. When you were sending me the messages, I was over here. So. All right, so that same thing applies. Now, I know I'm kind of going a little bit out of percentages, but the answers are percentages. So I'm taking this liberty to use percentage because they're the answers. The percentages. Everything is a percentage. You are going to use, everything's got to be multiplied by 100 if you're going to use a percentage. And if you're getting the percentage of one value, if you're getting the percentage of a value, you multiply it. Usually, again, with chemical addition, you're going to be dividing by the decimal as a percentage. I don't have any of them with me here. What is the grade? Oh, we are going to do a grade problem. Slope over, drop over, run. Oh, okay. No, that's cool. Because that's actually a collection system favorite. Slopies equals rise over run. Okay, so the next problem in this little cavalcade of math problems that I have is it's a similar problem, but it's different. It's the same but different. Does that make sense? No, it doesn't make sense at all, right? And I don't know if you guys can read this. I'm on my phone and I'm having trouble. Oh no, it gets bigger. It gets bigger. I can get it to bigger on my phone. If you guys haven't done that, if you're on your phone and you can't read it, I don't know what kind of phones y'all got. Let me just do this. Because I like to see what you're seeing. Because it doesn't profit either of us if you can't see what I'm saying. All right, so, oh, I hate myself. Anyway, if you got your phone, right, and you want to, oh, it doesn't work. See, it doesn't work with the video or the picture, but it does work with this. So let me do this. All right, now you see it's small, right, but you can make it bigger on your phone. I don't know if you guys see that. You can make it bigger on your phone so it's easier to read. I just figured that out. Wow, look at me. Anyway, I don't know if it's the same on, I don't know what you guys are using, if you guys are using phones, if you guys are using computers, but if you are using a smartphone, then you can do that. You can make it bigger. All right, so the next problem, this is, it's kind of the same problem, but the values are different. All right. And it's the same dilemma. Let me read it. Okay, if 125 pounds of magnesium hydroxide, I think what the heck magnesium hydroxide is. It's not milk of magnesia. I can't remember. Is it milk of magnesia? No, that's magnesium sulfate. What's the common name for magnesium hydroxide? It's hydroxide. Let me just look it up. Anyway, it says if 125 pounds of magnesium hydroxide. Wow, I can't remember what it's for. Let's say magnesium. Hydroxide. Is it milk of magnesia? It is milk of magnesia. I was right. I thought it was magnesia. All right, which is also another additive for alkalinity. Milk of magnesia. So it gets things going. Anyway, if 125 pounds, it's actually a pretty stable chemical. I couldn't remember. I thought it was milk of magnesia. Sometimes collection systems add this to they spray coat this for on a crown spray to stem corrosion from hydrogen sulfide. But anyway, it says 125 pounds of magnesium hydroxide are dissolved in 15 gallons of water. What is the percent strength of that solution? It's the same problem with different values. Now, remember I said the magic of the metric system was with water, it's pretty straightforward. 1 liter of water weighs 1,000 grams, which is the same as a kilogram, and it's also the same as a milligrams, and that's why milligrams per liter, it means a part per million. It's a little different. What is it called? The empirical system? The English system I used to know it as. You know, inches, feet, yards, pints, quarts, gallons, that kind of stuff. But there is a conversion of gallons to pounds. It's a pretty common one. Imperial, thank you. Remember the margarine they used to sell. Remember the Imperial and the crown would appear on the head? It is Imperial. Okay, thanks. All right, so the problem kind of is the same. Like I said, same but different values. Instead of grams, it's pounds. Instead of liters, it's gallons. There is a conversion for that. And that conversion is 8.34 pounds per gallon. I say, wow, you knew that quick. I've been doing this for a while. But even not a while, that's a conversion that you will have tattooed in your brain. We use it a lot. It's going to come in handy when you're doing what's called the pounds. I grew up, it was called the pounds formula. I think on the ABC formula sheet, it's called the mass flux formula. It kind of sounds something from Marvel. But it's also called the mass flux formula, the flux formula, depending upon what you're. It's a primary formula if you're calculating chemical dosage. It's also a primary formula if you're calculating pounds of BOD or pounds of solids. It's a very common formula. It's mg milligrams per liter times 8.34 times mg day. That 8.34 is the weight of water, pounds per gallon. So in the business, if you go up to somebody in water or wastewater and ask them what 8.34 pounds means, if they don't know, you have my permission to slap them. Especially any people that had me that was in my class over the last 10 years. And there's a lot of them at the valley. Just go up to them and says, Coop asked me to ask you what does 8.34 mean? They should know. No, you don't want to slap them. We don't want to encourage violence, you know. But at any rate, it's a common popular thing. You should have it tattooed in your brain, 8.34 pounds per gallon. So that's the conversion. But it's the same problem otherwise. So again, it's a magnesium hydroxide, and determined it is milk of magnesia. It's a powder chemical. It's kind of like chalky. It would be added, say, for alkalinity addition. Collection systems sometimes use it as a crown spray chemical to coat the inside of the pipe to prevent corrosion from H2S. Not that commonly used, but it can be used for that. Because it's better than, say, adding hydroxide, because hydroxide just goes downstream. It raises the pH, but it's only temporary. A hydroxide, magnesium hydroxide sprayed on the pipe will stick there for a little bit longer, so it'll help to stem some corrosion from H2S. So anyway, 125 pounds of magnesium hydroxide are dissolved in 15 gallons of water. What is the percent strength of the solution? Is it 45%, 50%, 55%, 60%? Now, remember, a gallon of water weighs 8.34 pounds. So you can incorporate that into the solution, into the solution to the problem. All right, so I'm going to go do it up on the board. Should have erased this while I was bloviating about this problem, but I didn't do that. Now I'm jumping right into chemical stuff and dosaging and all this other nonsense, but we are going to build a house and we are going to lay some foundations. And actually, some of these numbers are some foundations that you're going to have to remember. So that's why I kind of do it this way. And again, we repeat ourselves. People remember stuff if they hear it over and over and over and over and over and over and over again. So that's what I'm kind of doing here. Actually, did somebody shoot me an answer already? Let's see. Imperial. Da, 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 da. There was a margarine commercial. Remember that? I don't know if you guys, maybe you know. Got to remember, I'm 62 years old. I actually ran into somebody today that had just turned 62, so I told him, welcome to the club. Anyway, guy Harry from Bayshore Region. I knew him for years, but I never really got a chance to chat with him. Today I got a chance to chat with him. Good guy. Really good guy. One of the students from Bayshore. Actually, a couple students from Bayshore. When I toured that plant with them, we kind of had a sit down, and I saw him at the seminar today. And told me he just turned 62. Anyway, looks better than I do, quite frankly. Okay, so let's do the same thing. We'll do the knowns and the unknowns. Again, it makes it easier for me to do it this way. Hopefully it makes it easy for you. Now, I'm probably not going to write the right chemical formula for this. I'm going to try. I don't remember what it is. I think it's MgOH. I'm not sure. That sounds like what it should be, magnesium hydroxide. So that's a known, 125 pounds of magnesium, and I'm going to put an OH here. I don't know if that's right. You guys can check it out like you did for calcium oxide. Where is it? Magnesium hydroxide, and it's dissolved in 15 gallons. And I'm going to shorten that of water. Okay. Ooh. Oh my. 15 gallons of water. And the solution is solution strength, percentage solution strength. So what's the percent? What's the solution strength in percentage? Okay, so here we go. Now, I'm just going to do it this way because we already did the weight, but we got to figure out what the weight is. And then you're going to multiply it by 100 to get that weight, but I'm going to show you. So we know the weight of the milk of magnesia is 125 pounds. So I'll skip the weight, and just fill in the numbers. Now this is 125 pounds also. You're going to add that to the weight of the water, which we haven't figured out yet, but we will. That's going to be the equation, the weight of the water. Now, I'm going to be doing these conversions, so here we go. All right, so we have 15 gallons of water, right? That's what we have. I write the conversions this way. You can figure out your own way. This, to me, works best. All right. 15 gallons of water. You can write it with a little line, make believe it's a little fraction there, a little over and under, right? Little numerator and denominator. Now, there is a conversion, and I've said this. We have gallons. We want to get to pounds, but we don't know what those pounds are. We know that there's 8.34 pounds in every gallon. So there's 8.34 pounds in every gallon. We do it this way because we want the gallons to go away. We want to be left with pounds. So they go on opposite sides of each other. We're left with pounds. So this is going to tell us what arithmetic we're going to do. So it becomes 15 multiplied by 8.34. you're gonna be left with pounds. You're gonna be left with pounds. And then, of course, you're gonna multiply that by 100, but. So 15 times 8.34, whoops. 15 times 8.34. Can you see that? 125.1. 125.1. So that's what this is. 125.1. That's the pounds of agua. Agua fria. Agua fria. Pounds of water. So let's add that. The 125 becomes 250.1, right? So 125 divided by 250.1 multiplied, Malaka, 125, I hit the wrong button. 125 plus 125.1 equals 250. Come on. I'm having issues here with my calculator. My trusty rusty calculator isn't so trusty tonight. Right. So 125 plus 125.1 equals 250.1. 125 divided by 250.1 equals, what does that equal? 0.4999888, whatever, right? So we multiply that by 100. $49, almost 50%. So the answer choices are 45, 50, 55, and 60. We got 49.98%. 49.98%. What's the closest answer then? I would say it's 50%, right? 49.98. Rounded up, it's 50%. As we all say, it's good enough for government work. 50%. To figure this out, this is the most vital part. Knowing that 8.34 pounds is a gallon, right? Because you have the pounds of the chemical. Now, yeah, I guess you could pour the powder into a 15-gallon bucket to see, but it's not going to be consistent. But so you convert the volume of water to mass of water. Oh, I can't believe it. Did I just do this and the camera wasn't on? Oh, no, it's on. Oh, it isn't. Okay, no, it's on. Oh, it's to the, you know what I gotta do? That way, I'm not blocking the board. You need to look at this, not me. Okay, so when you're getting the solution, the concentration, or when you're figuring out the concentration of a solution, you include the water that you're using to make up that solution. And then of course, you would calculate that if you're adding it to for the effectiveness of a process. That would be the next level of calculation. Right. But usually, like magnesium hydroxide, powder chemicals are usually purer of the actual chemical that you're going to use. At least these are. It's actually going to react. This is just water, folks, so. Anywho, good. So let's do the next one. Yeah, we'll do the next one. Actually, I think the next one, it gets cut off on the bottom, doesn't it? Oh, no, it's all there. It's all there. It gets cut off on my screen, but it doesn't get cut off for you guys. Okay. I know I'm kind of jumping ahead in terms here. I gotta stop and do a little explanation. I'm gonna read the problem, and then I'll show you what they're talking about. It said, how efficient is a pump? Because these are kind of introductions to things that we're going to talk about down the road. How efficient is a pump if the output power is 1.77, and they have here water horsepower. I'll explain that in a second. And the input or the brake horsepower is 250 horsepower. And then the answers are in percentage, so you know you're multiplying it by 100. Now, mathematically, this is very simple. 1.77 divided by 2.50 multiplied by 100. But if you don't understand the meaning of the terms, it's meaningless to you. Okay, when a pump is operating, right? There's essentially three horsepowers to a pump. Okay, one, water has weight, right? 8.34 pounds per gallon. We just did it before. Water has weight. When you put something that has weight into motion, you know, using kinetic energy or whatever, you're going to develop something. You're going to develop power. All right, you're going to develop horsepower. So water horsepower is set to a flow, which is gallons per minute, multiplied by something called TDH, total dynamic head. It's the flow multiplied by the resistance that that pump is going to meet. That water, I should say, is going to meet. What resistance is the water going to meet? In the form of what's called head pressure. There's two forms. There's static head and there's dynamic head. Static head is the height that the pump just basically has to lift the water. The total dynamic head is the static head plus friction loss in the pipe, restrictions in the pipe, flow meters in the pipe, bends in the pipe, all of that stuff, all of those, the lining of the pipe. If there's corrosion on the inside of a pipe, that's resistance against that water. That stuff makes a difference. In this particular problem, it says to meet the demands of the flow with the head requires 1.77 horsepower. That's the water horsepower. That's just the water going through the pipe. If you want to see the demonstration of water power, anybody that works in Zimpro, I don't know if we've ever fixed it. We've tried many different ways. I think Mark Taylor had them put, I didn't agree with it at the time, but I think it worked. The dewatering line in Zimpro, the dewatering line that runs from the heat treatment plant from Zimpro to the thickeners. Every time the dewatering pumps would kick on and kick off, that whole pipe would shift back and forth because of the surge. And a lot of it has to do with that water, once it's set in motion, the weight of it, and then if it stopped somewhere along the line, that water wants to come back. And it would slam into the back end of the check valves. But that power of that water coming back and forth would literally move the pipe. And that's a pretty big pipe. If you guys know the pipe I'm talking about, it's a huge, I think it's a 12-inch pipe. I think it's 12-inch, might even be bigger. It's a stainless steel pipe. There's an expansion joint at the east side of Zimbro near the ceiling. I'm trying to think where the other expansion joint is. It might be in the thickeners. It goes to an elbow that goes upstairs to the distribution box, the main distribution box. There's also a cutoff at T that it kind of sends it to the STSR line, which I hope they didn't reopen it. But anyway, when that water moves through that pipe, right, and then it stops, all of the weight of that water wants to go the other way. It's like a giant wave. And we used to literally physically see that pipe, that expansion joint, slam and open because of the weight of the water. That's the water. That's the power that water has. Underneath the maintenance office, I guess I don't know if that's where Leach is now, in the thickener building, where Gene Liswan used to be, and then Bruce Green was there. And then I think when Gene got promoted, then Bruce took over. I think by Dave Leach's office and Gene's office. Underneath that, his office near the ceiling, they used to hear the pipe bang where they were. Now, the pipe was designed to move. It's on pipe hangers with rollers, so it was designed to move. Then somebody came up with the idea. Actually, I think they called a consultant in to stabilize that pipe by welding it to the beams, by bracketing it to the beams with welds. And you can ask Joe Benson about this. If anybody knows Joe Benson, he was a contract welder at the time. He wasn't working for Passaic Valley at the time. He worked for, I don't know if it was Cortese or Sam's Tube End, whoever it was, but they told him to weld the stainless steel pipe so that it wouldn't move. And Joe said to me, he said, "This is a really bad idea." And it's like, yeah, I know, Joe. They set up the scaffolding and he did it. And him and Pete, you guys know Pete Lopez, excellent welders. The both of them are top notch. But anyway, they did it. They did what they were told. And the pipe, now you have a stainless steel bracket hilted into the column, welded to the stainless steel pipe, right? It ripped the pipe like it was a zipper. It ripped the pipe open the first time it shifted. So that shows you the power that water has, right? So to move a certain amount of flow, a certain distance with a certain amount of resistance, again, that formula is going to be for the water horsepower. It's going to be GPM, gallons per minute, multiplied by the total dynamic head. And then the number is going to be divided into 3,960. So where the heck did they get that number for? It's a rounded up number, but essentially it's 33,000 foot-pounds per minute, which is a horsepower, 1 horsepower, divided by 8.34 pounds per gallon, which is the weight of water. That's where they get that 3,960. If you do that on a calculator, it's actually 3,956. I don't know why it's rounded up, but that's the standard formula, GPM times TDH over 3,960. That's the water horsepower. So when a horsepower is designed, the water horsepower is going to be the least of the 3 horsepowers. It's just the water in motion. It's just how much horsepower, how much power you have to apply to that water to move that water at that flow with that much resistance. That's just the water horsepower. That's the water in motion. Going through a pump, and this says, and it's kind of deceiving the question, it says the input shaft, or the input, or the brake horsepower. That's referring to the shaft between the motor and the pump itself. We know that the components of a pump, there's a motor, then there's a pump itself, right? There's the shaft, then there's the power frame with the bearings, the seals, the casing, and inside the casing is the impeller, and then inside that impeller is the water moving around it, right? So in order to move that water a specific distance at a specific flow, a certain amount of horsepower is going to be required. Between the water and the action of the pump itself, there's going to be loss of efficiency. So the input power to that pump has to be higher than the horsepower to move the water just by itself. And say, well, where does that come from? It comes from drag on the bearings. It comes from, especially if it's braided packing, it comes from the packing on the pump. All right. It comes from the inefficiencies of the impeller. When we get into pumps, I'll talk a little bit more about that, but there's basically no pump is 100%. And some pumps are way less than 100% because of what they have to move. So the input power to the pump is higher than the water horsepower. That's known as the brake horsepower. It's a resistance. There's a loss of efficiency through a pump. Depending upon the pump, it could be as low as 50%. It could be as high as 80%, but it's usually not very efficient because there's stuff that gets lost. Okay, so the brake horsepower is going to be higher. When you buy and when you order a pump, they usually, actually, I think you got to ask for it, but you'll get what's called a pump curve, which is, it measures the performance of that pump. And basically, if you look at the curve, and some of them are very complicated to look at, but if you look at the curve and anything below the line, the pump's running within its specifications. Above the line, it's running outside of the specifications. And that pump curve is the most efficient line of the pump of how it's running. Okay, but that's the brake horsepower. That's the brake horsepower. So when you operate a pump, the water horsepower is the lowest. Next is the brake horsepower, right? And then, of course, then there's what's called the motor horsepower. The motor horsepower is the electricity that's applied to the coils in the motor. The electricity that's applied to the coils to the motor. You usually see it as a box that sticks out the side where the conduit feeds the pump, the motor. That box is called a peckerhead. Not my name, that's what it's called. And that's where the three phases are wired to the coils, which spin that motor. That's going to be the highest horsepower, okay? Because that's the electricity that's applied to the motor in the form of kilowatts. And there's 0.746 kilowatts for every horsepower. We'll go through that when we do pumps. Okay, so the highest power applied to the motor. Motors are usually fairly efficient. You can get a motor that's 90% efficient, 80% efficient, 90% efficient. And again, there's losses because of usually bearings. There is a drag. And I know bearings are supposed to make everything straight and smooth, but just the fact that they're there, the shaft has to touch something, you're going to lose a little power through that. It's not floating in a vacuum, just spinning. So the input power to the motor is the motor horsepower. The input power to the pump, which is also the output shaft power on the motor, is the brake horsepower. That's how much horsepower has to be applied to that pump to move that water. And the lowest horsepower is the water itself that's in motion. What this question is asking, it says, how efficient is a pump if the output power is 1.77, aka the water horsepower, and the input or the brake horsepower is 2.5 horsepower? So you're there, and it's the answers are in percentage. So you're asking for a comparison between one and the other. So essentially, you're going to take the in, right? You're going to take the lower one and find out how close the lower number is to the higher number. So you're going to use division. I'm not even going to do it on the board. And then you're going to multiply that by 100. All right. So essentially what this does, you are taking Put the camera. I'll do it on my calculator right in front of y'all. All right, and then you guys can follow suit. Just so that I can see what I'm doing. All right, so got my old calculator out. What was it? 1.77 divided by 2.50 equals. Yeah, you can see that? 1.77 divided into 2.50, 0.708. You multiply that answer by 100. I got to figure out what angle is most visible. 70.8%. Now, if you look at the problem, let's see which one is closest. It would be C, right? 70 is not there. It's in 70.8. 0.8 is higher than 0.4. So you round up to 71. That's the closest answer, 71. So it says, how efficient is a pump? The output power. Now, it's not a comparison of in minus out. It's kind of set up sort of the same, but you're taking the first number, and one of the tricks is it's lower number. Lower number in the numerator, higher number in the denominator, and that's how you do it. Now, like, as opposed to that in minus out over in, that's a measurement of what's retained. That's the difference between the two. So that's why you do the in minus out over in. This is a straight up efficiency of a percentage from one to the other. If that were to be the motor horsepower that they were asking for, that would be what's called wire to water efficiency. But it's not. It's the brake horsepower. They're just messing with your heads. But there is something called wire to water efficiency, which is the comparison between the water horsepower and the motor horsepower. Right? This is referring to brake horsepower. Right. Whoop, whoop. Everybody say whoop, whoop. Anybody whoop, whooping out there? I hope so. I'm just all whooped up. I am. Okay, so, but remember, when you're dealing with percentage, you got to get it into a percentage. So you're always going to multiply it by 100. Okay, it's usually the lower number over the higher number. Now with solution, you're going to include the water that makes up that solution as part of the formula. So it's going to be the chemical over the chemical plus the water to get the percent solution. Then you multiply that by 100. So you can write something down on the paper what the percent solution is. See, if you listened and see, that's for Patty, so she could know that you paid attention to what she told you to do. All right, the percentage. And percent removal is in minus out over in. Now, if you're trying to find the percentage of something, or if you're trying to determine what number is the percentage of something, then it's multiplied. If you're, and I didn't do any here, but we will. If it's a purity of chemical issue, you divide by the percentage as a decimal. Everybody said, whoop, whoop. I spent a lot of time on this, which is good, I need to spend time on this. Actually, we got more. We got a couple more. Yeah, I got another page of these. I didn't realize that, but I do. Let me get up here for a minute because I got to keep track of my papers. I don't want to lose my papers. So you could look at that for a minute. All right. So I got a few more of these problems. As far as the percentage of percentages. not persimmons. Persimmons is a fruit. But percentages of percentages. Come on. Okay, now this is in percentage as well. I'm going to read it. Let me tell you what, let me take my camera off because I don't want to be a distraction from what we're reading. Another explanation is in mind here. Okay. It says, what is the grade if there are a rise of 3 feet and 300 feet is the run? Any idea? Anybody know what he's talking about? Wait a minute. I didn't catch that message. You don't have to speak up. I just got a minute to read. Hang on a second. Beautiful. No, not quite. We'll get there. We'll get there. Let me just, I didn't catch that last message, my friend. Oh, no worries. No worries. No worries. You do what you need to do, my friend. You take care of that. No worries. I got the recording for you. No big deal. And yeah, John, you're right. John Tran. Yeah, exactly. Yeah. There's actually a value there. Yeah, Tony, you're right too. It is rise over run. Rise over run. Thank you. Thank you. Cool. Cool. This is a common collection system math problem. I'll do more later on, but this is a common. But because this is a percentage, that's why I included it into the percentage stuff. So yeah, you guys are absolutely right. It's rise over run. I like to use rise over run because it's, I don't know, it's poetic. It's, I like ours, I guess. Because some people say rise or drop over run, and that's fine. That's fine too. That's exactly what it is. And I know a lot of you maybe don't know, but there's really nothing to change. If the grade of a sewer, all right, there are certain grades that are required for a sewer. You're supposed to maintain 2 feet per second, half full, as your good velocity in a sewer. That's in the perfect world. But I know we don't live in a perfect world. But that's initially what sewers are supposed to be designed for. 2 feet per second is the velocity, 2 feet per second, half full. That way, one, there's room for it to go up a little bit and do a little bit more scouring. If it goes down, it's still not really a big deal as long as you meet that 2 feet per second, at least during your daily peak flow. But essentially, that's supposed to be the average daily flow. It's supposed to be 2 feet per second, half full. You say, why half full? All right. A full sewer is going to surcharge, and it's not always going to be that way, right? It's not always going to be that way. And you guys are absolutely right. It's rise over run. That is slope or grade, right? That's exactly right. So actually, I'll do it. I'll do it on camera if you want. I don't have to go to the board for this. So anyway, this is a kind of a common problem that comes in on collection systems tests. You know, you might get a couple of these. All right, and essentially what it is, the elevation difference between two manholes, or the chambers, basically the invert of the chambers, like Tony had said. He said manholes. That's kind of the 300 feet is kind of like one of the standard distances between manholes, 300 feet. And if there's an elevation difference, and it's measured by the invert, actually, the invert, which is the bottom part of the chamber. The elevation of one compared to the other, the difference between the two is the drop or the rise. I say rise because it just goes nicely with rise over run. All right, and that's how you figure this out. It's 3 divided by 300. And sometimes people get lost in the decimal places. So you have to make sure, because this is a percentage, you have to multiply it by 100. Do you ever go down a mountain or up a mountain and you see these nice little signs where they'll say 4% grade, 5% grade? That's what they're referring to. They're referring to the elevation difference between the top of the hill and the bottom of the hill and the distance. It's like you take a triangle and the run is the distance between the 2 points on a straight line, and then the difference in the elevation between the 2 places. So it's 3 divided by 300, and you just forgot to multiply it by 100 because you had 0.01, which if you weren't multiplying it by 100, because it's asking for the answers in percentage, then you'd be absolutely 100% correct. But you got to, the answers are in percentages. So you got to multiply that by 100. So it's 3 divided by 300 multiplied. 3 divided by 300 multiplied. How come I can't? You guys can't see that. Why can't you see that? How's that look? It doesn't look good on my screen here. Alaka, yeah. Let me take this off. Maybe it's the. Let's see. There you go. Answer times 100 equals. So that's a 1% grade. As compared to, sometimes you'll get it in percentage. Sometimes they won't ask it in percentage, but you got to look to see if they're asking it for you in a percentage. And that's when you multiply by 100. I didn't get to do that on the board. But it's an elevation difference between the two. An elevation difference. All right, so let's like hit the next one. And this kind of speaks to the difference between the comparison between pure chlorine and calcium hypochlorite, also known as HTH. All right, so let's read this. Hey, my camera won't show up. I don't want you guys to see me. So let's read it. Oh, the arrow does work. Okay, so it says, how many pounds of chlorine are there in 8 pounds of calcium hypochlorite that has 70% chlorine? So you're given the, basically they're asking you, what's the percentage? What's 70% of 8? That's what they're asking you. You're going from pounds to pounds. It would be the same as if you were, all right, here's 8 pounds of powdered chlorine. That's what calcium hypochlorite is. Now they have 70%. This is a waterworks question, I think. The reason I say that, yeah, it's 8 times 0.7. Exactly, Ron. You got it, man. And then you should have the answer. So it's the same thing I was asking, what's the percentage of chlorine? I'm not even going to do this one on the board either. So it's 0.70 times 8, because it's going to be less. Right, because you're looking for the chlorine, and you know that the calcium hypochlorite is not pure chlorine, so it's going to be less, right? 8 pounds of hypochlorite does not equal 8 pounds of chlorine because it's only 70% pure. So you can eliminate D and C completely. You can wipe them out, just by knowing what calcium hypochlorite is. Now, normally, the numbers, the most numbers that I've ever seen with calcium hypochlorite is 65%. That's been the answer, but this has it as 70. I'm not going to fight that. Okay, so yeah, it's 0.70 times 8. But you can look at these and eliminate D and C. Because if it was C, that means it's 100% pure. If it's D, it's more than 100% pure. Exactly, Tony. Beautiful. Thank you, sir. For everybody else, it's 5.6. For 5.6. And I don't know, maybe you're sharing these messages with everybody. Oh yeah, everybody's seeing them anyway, because you guys are all getting the same messages, which is good. And I applaud your bravery, I do. Because if you get it wrong, then everybody knows you got it wrong. But there's nothing wrong with that. We all kind of learn together that way. Don't ever be afraid of being wrong. I mean, I'm wrong a lot, so don't ever be afraid of being wrong. Okay. So yeah, he's absolutely right. Tony's right, Ron's right. It's 5.6. Who else? Somebody else. Rise over Ron. Tony Cassiano, Ron. Good, good. Thank you. So yeah, it's 5.6. It's basically 70% of 8. And you got to remember, of course, because it's not pure. It's not pure. It's not going to be 8. And it's not more than pure. So it's not going to be 9. Then this next one is kind of a funky one. It says, during a closed circuit television inspection, it was found that 23 out of 90 joints had excessive infiltration. On a percentage basis, how many of the joints were faulty? So it's asking you, okay, it's a percentage, so you got whatever you figure out, it's going to be multiplied by 100. Right? So it's saying that 23 out of 90 are bad. So what is that in a percentage? How would, like we would know that 45 would be 50%, right? So out of 90 joints, there were 23 of them bad. Now, what they mean by excess infiltration. Infiltration is groundwater that makes its way into a collection system, a sewer system. Most of the time it comes from bad joints. Whether it's a crack joint or, we usually crack joint. If it's going to be in the middle of the pipe between joints, it's probably roots. Okay, but the roots will even find their way into the joints easier. Okay. Infiltration is groundwater making its way into the sewer. Inflow is water from the surface making its way into the sewer system. Both are really bad. If you have excessive inflow and infiltration, it could limit the ability to have service connections. So like the developers won't like you. If you have excess infiltration, you got to do something about it. There are a couple of methods, and when we get into collection systems, I'll mention them to you. Internal grouting, which is pretty cool, where they actually send a little trolley, a little tractor in there that has 2 bladders on it, and then it's connected to a grout injector. And as it goes down the pipe, it's monitored by a camera. It goes down the pipe, the bladder expands by the joint, and grout gets jammed into the joints, sealing the joints up. And what did you say, Adam? 23. Did you say C? It is C. Thanks. And this problem is 23 out of 90. 23 divided into 90 multiplied by 100. And yeah, it's 25.6. 25.6. Groovy. So you guys are with me. Thank you. I appreciate that. So that's how you do that. 23 divide 90 equals something, and then you multiply it by 100. Always multiply by 100 if you're yielding a percentage from regular numbers. Remember that one. Sometimes it's a little confusing. Well, what do I do? Do I multiply or do I divide? This is a comparison, if you read the question, during closed circuit television inspection, which are quite common. Right? It was found that 23 out of the 90 joints had excessive infiltration. On a percentage basis, how many of the joints were faulty? 23 divide 90 equal multiplied by 100, and you should have got C as the answer. All right. All right. Now the next one, number 4, is a little funky. It's similar to the previous one that we did before. It's pretty much identical, only this one isn't so easy. Because it could be multiple answers. And it's kind of the same thing. And you can, when you see a problem like this, you can put into it what you need. Right? Because it doesn't tell you what it is. It could be liters per minute, it could be gallons per minute, it could be gallons per day, it could be whatever it is. 288 is 70.3% of whatever this thing's doing. They want to know what is 100% doing. Now, I always set these things up the same way. It's just easier for me. So it would become, to me, it's 288 multiplied by 100 divided by 70.3. Oof. And you're going to get one of those answers. Now you can set it up with the lines, right? It could be 288 over 70.3 equals 100 in the denominator over, I don't know, on the top, cross multiply. 288 times 100, obviously that's, what is that? 288, no, 28,000? 288, yeah, 28,800 divided by 70.3, and you should get 409.6. 409 is not there as an option. So the closest answer would be 410. What did I do? Did I shut myself off? No. No, I don't want to view everyone. I just want, I want to be the biggest man. There you go. So that's how I did it. The lighting is terrible. There we go. I got a good lighting there. Groovy. Let me just catch up on the messages because you guys are sending me messages and I really think that's cool. Really think that's cool. And I'm going to finish up the last one here. I'll let you guys kind of figure this one out. Don't be intimidated by the terms they use, okay? Do not be intimidated by the terms they use. Let me pull this one up. It's the last one on the page, and then we'll call it a night. Does it cut off on the? It does kind of cut off. Let me shut my camera off. All right, so I'm going to read it. And think of in minus out over in. Think about that. That's what this problem is. They just changed the terminology. That's all. So the iron, ferrous, content of a water source averages 0.81 milligrams per liter of iron. What is the percent removal? There you go, in minus out over in. The treated water averages 0.01 milligrams per liter of iron. Percentage, no, you get the percentage because you multiply it by 100. I already did an in minus out over in. It becomes 0.81 minus 0.01. Which gives you 0.8, right? Divided by 0.81, which gives you what? Now this is where, this is definitely American Water Works Association question. did you remember I mentioned about this whole rules of rounding stuff? That's where this comes into play. The choices are 96%, 97%, 98%, 99%. It is definitely a waterworks question because they do that. The Water Environment Federation, many times their questions are going to be, the answer choices are going to be so out of there. It's easy to find them. American Waterworks Association does it all the time in their review guides. They'll give a problem and then everything will be so close together, 96, 97, 98, 99, they make you work for it. Now, if you do that problem, right, 0.8 minus 0.01, which equals,
Would it be D?
then you divide into 0.81. Did you say D?
Yeah.
Exactly. You round up because you get 98.7. So if you see a question like this and the answers are really close and you get a decimal, you got to pay attention to make sure that you round properly. If it was like 98.4, then the answer would be 98.4. Or the answer would be 98. 98.5, you round up. I know that because it's 0 to 4, you stay down. If it's 5 to 9, you round up. And you would do that again because look at the answers too, 0.81, 0.001. So they're taking it to 2 decimal places. All right. Now the answers, there are no decimal places. There's basically 2 significant numbers without a decimal place. The answer that you get on your calculator is like 0.987 multiplied by 100. It's 98.7, like your temperature. Actually, it's almost 98.8 if you round up with those numbers. So the closest answer in their choices is 99%. And that's where they get you sometimes with the rules of rounding. So the closest answer to here is 98%. 99% because it's 98.7. Don't get fooled, okay? Because it says 98.7. It's not 98%, it's 99%. Groovy. But remember, always with a percentage, that 100's going to play in there somewhere. It's definitely going to come to play. So you got to incorporate it. You always multiply by 100% when you're dealing with percentages. If you're yielding a percentage, it's going to be 100. You're going to multiply by 100%. Okay, so I'm just going to read this and then I'll hook it up for you next time. I'm not going to. Oh man. And I'm going to kind of call it a night because I think you guys are burned out. No, I am. Camera. I'm just going to read this for the next part. And then we'll hit these problems next. Actually, I don't think there's too many problems with this. Okay. So the next subject, which I'm going to leave, what's today? This is Tuesday, so I'm going to leave it for Thursday. I'm going to talk about perimeter. Perimeter is a linear measurement. And we'll get into this when we talk about I'll say weir overflow rate is an important function of perimeter. And also, if you want to paint a building, it's an important function of perimeter. If you want to paint a tank, you're going to use the perimeter. You're going to use the distance. It's a singular number. It's like we usually deal in feet, but it's needed to determine the area. That's part of it. If you're going to determine the area, especially a cross-sectional area, later on when we're calculating velocity and flow, you're going to need the perimeter. It's helpful, especially with a circle. Okay. Now, in a circle, it's known as the circumference. Now, one of the phrases that you hear about is pi, not apple, not blueberry, not lemon, but pi. It's a constant with circles. This is where this kind of comes into play for certain
questions. All right. I always just use 3.14. You can use a lot of decimal places, but I always use just 3.14. I kind of cut it off there. Every circle in the universe will yield pi, 3.14. Essentially, the circumference over the diameter is pi. So inversely, if you need to find the circumference and you have the diameter, it becomes pi times the diameter will get you the circumference. Okay, but every circle in the universe, it's pi is the circumference over the diameter, the distance around the circle divided by the distance across the circle. So if you have the diameter, you need to find the perimeter, you just multiply 3.14 times the diameter, and that's going to give you the circumference. But it's needed in determining the area. If you were given it, if you're given the perimeter, you can determine the diameter if you're using the cross-sectional area. Okay, but it's one value in a series of values, and we'll get into this. So this is the perimeter. It's used for the weir overflow rate. All right. 3.14 is the constant known as pi, is defined as the circumference divided by the diameter. This number can be expressed in anything, inches, feet, centimeters, meters. We're predominantly going to use feet. Now, for the weir overflow rate, that's a common loading for clarifiers, and you use it's the gallons per day divided into the linear length, the length of the weir, whether it's the perimeter or the outside area of the weir, but you use the linear measurement of the perimeter in a circle. But it's called weir loading rate. I'm just, what the heck is it? 1,000? No, I'm sorry. Weir loading rate is the higher one. I got my signal crossed for a minute. That the expectation of a weir loading rate on a clarifier is anywhere from 10,000 to up to 20,000 gallons per day per foot. The normal range is 10 to 14, but it should be less than 20, but it can be 20. 20,000 gallons per day per foot of weir. So for every foot of weir, the expectation for a weir loading is to be at least 10,000 gallons a day over it. And that's a design parameter. That's one of the parameters that a clarifier has to fit into. One of the other ones is surface loading rate or surface settling rate, which is gallons per day per square feet. But that's the area, the surface area of the tank. That's usually around 1,000, give or take, 1,000 feet, 1,000 gallons per day per feet. Okay, but these are common loadings for clarifiers. Okay, and part of that is that weir length, and it involves a perimeter, especially the perimeter of a circle. Okay, and then we'll do these problems next time. Actually, that's all I got. Oh no, I got some perimeters. And I am going to call it a night for tonight. I hope I didn't burn you all out too much. So let me, I appreciate I do appreciate the feedback from everybody tonight. That was much appreciated. I know guys are